So rough definition, a power function is anything that can be written as kx to the p, where kp are real numbers, p we call that the power, k we call it the leading coefficient, and we call x the base. But k is very important. We talk about leading coefficients a lot in this section and throughout the next couple of ones. So what's kind of interesting about power functions is it's not really different every time we draw a graph. What that means is that if I have anything that's an even power, I have this picture of this graph right here. These are three different graphs. One of them is red, one of them is blue, one of them is green. Do I label them? No, I don't. One of them is x squared, one of them is x to the fourth, one of them is x to the sixth. So they do look a little bit different, obviously. But something that's worth noting is that they all seem to be doing the same thing when we go all the way to the left of the graph and all the way to the right of the graph. And we can see that again with odd powers. The first odd power that we have is in this graph, just y is equal to x, which looks very different from the other graphs. And then I believe one of them is x cubed, one of them is x to the fifth. And aside from the fact that, yeah, they do look different, especially kind of close to the origin, is that the end, they are going in the same direction. So as I go to the right side of my graph, all of those graphs go up. And as I look towards the left side of my graph, all of those go down. And so that's kind of cool that these follow a pattern. Anything that has an even power will either go all up or all down, and anything that has an odd power will kind of flip sides. So we kind of gather that information in this table. And these are the only four cases that we'll see. We'll have even powers where your leading coefficient k is positive, where it's negative, and then we'll have odd powers where it's positive or negative. So in the previous slide, we saw the positive cases. So if an even power is, we have a leading coefficient with an even power that is positive, then we have kind of the classic parabola or graph that looks like that. And so if we talk about end behavior, it's kind of maybe a little overwhelming looking at this table at once. So let's just look at the very top left box that has that x squared graph in it. When we talk about end behavior, we say as x goes to infinity, which means as I go to the right side of my graph. That's a really fancy way of saying as I go to the right side of my graph. So when we look at this, as I move to the right side of my graph, well, my graph goes all the way up, which is, it's going to go forever, all the way up to positive infinity. Now, if I look towards the left side of my graph, the same thing happens. My graph goes up, 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 so it goes all the way to positive infinity. And so that's how we talk about end behavior. And if you go into calculus later, you will see this notation a lot. Is yes, we're talking about as x goes to infinity, what's happening to your graph? Well, as we go to the right side of the graph, what's happening? And as x is going to negative infinity, as x is going to the left side of your graph, what is your graph doing? Is it going up? Is it going down? Is it staying at the same value? So to see that again, I think we go stick in the even powers we do. And so we can see this again on the bottom left graph now. We're saying, okay, what if I have a graph with an even power with a negative leading coefficient? Well, it's the exact same graph that we saw top left, except for flipped. It's a negative in front. So everything is going down versus going up in this case. So again, as the phrasing goes, as x goes to infinity, f of x goes to, well, in this case, negative infinity, goes all the way down. And as x goes to negative infinity, f of x goes to negative infinity again. Both of them are going down. Moving on to the odd powers. Odd power, as x goes to infinity, we can see that in this graph, goes to positive infinity. As x goes to negative infinity, f of x goes to negative infinity. And then if we flip the sign, if we make k negative, that flips our graph and we see that as x goes to positive infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to positive infinity. Now this is, again, a little bit weird and a little bit overwhelming with notation, but this is kind of what we're asking when we are writing an answer to end behavior. Yes, it's important to know the concept, and yes, when we get into graphing, the concept is much more important than this notation, but this notation is common. So if I were asked a question that was like, what is the end behavior of this graph? I would always be saying as x goes to infinity, and then I would describe what's happening with my graph. And I would say as x goes to negative infinity, I would describe what's happening with our graph. So it is that kind of what filling in the blanks did when we went through this slide. Now, to kind of see this in practice, I kind of shrunk down the table so I have a little bit of space to look over a question. This question says, describe the end behavior of 2x to the 6. Now, it doesn't really matter exactly what the graph looks like. That's not what the question's asking for. If you have a graphing calculator, great, but I wouldn't even want you to sketch a graph. Instead, I would want you to identify things on your table. Okay, well, 2x to the 6, that's an even power. My k is positive, it's positive 2. And so I can look at my chart and see, okay, as x goes to positive infinity, my graph goes to, well, oh, I guess I went with negative. As x goes to negative infinity, my graph goes to positive infinity. And as x goes to positive infinity, my graph also goes to positive infinity. So this is kind of how we're going to start seeing this applied, is we're going to actually look at a function and then relate it back to where that falls into our chart. See this again. Now we have negative x to the 7th, and it looks like I don't have the leading coefficient, but in this case there is kind of that invisible 1 in front of my x to the 7th. So I have an odd power. I have a negative leading coefficient. It's negative 1. And so I look at my chart, and the chart is the bottom right thing. So now my answer would be, as x goes to, what do I start with? As x goes to negative infinity, f of x goes to positive infinity. And as x goes to positive infinity, f of x goes to negative infinity. And you could start either direction. You could say, typically kind of the standard is that we talk about the left side of the graph, then the right side of the graph. You could do right side of the graph, left side of the graph, or as x goes to negative infinity, describe your graph, and as x goes to positive infinity, describe your graph, or you could flip it as x goes to negative infinity like we have written here. Really, the important thing is you're saying what's happening on the left side of the graph. I'm going to describe f of x there. What's happening on the right side of my graph? I'm going to describe my f of x there. Whew, that's a little bit long-winded. Okay, moving on. Polynomial functions. So this is a very general form, but we see polynomials again and again and again. I still see polynomials in kind of my graduate courses because it is kind of the standard or the general form of the way that we look at numbers. A lot of things, a lot of functions fall into this category. And so some notation to talk about is when I have this polynomial function of this kind of weird form of variables flying around and anything like that, the biggest power, my nth power, is we call that my degree. We call my leading coefficient is that k. And then the red thing should say leading term, not leading coefficient. But really the important thing is degree, and then we already saw this before that the leading coefficient is k. And the reason why those things are important is we're going to tie this back to the polynomial functions. But for starters, before we get ahead of ourselves, let's just talk about identifying these terms. So I want to see what my leading coefficient is and my degree. So looking at this question, okay, the highest power, I have a constant term, I have x to the first, I have x to the 6. So my degree is 6. And then my leading coefficient is always what's next to that highest power. So I don't really care what's happening with my other terms. My leading coefficient is going to be negative 2. It's what's next to my x to the 6. Now, if you are going through a textbook that's very careful about how they're doing it, or you're reading over someone's work that's really good at simplifying things, they generally will write things in the form of highest power, then the next highest power, then the next highest power. Like that is kind of the standard way to write things. That doesn't mean that's always going to come out that way, especially if maybe you're doing some of your own work and you didn't rearrange it because you don't have to. Like you can write, if you were to simplify something in question B, that's a perfectly fine form. I'm not going to dock you if you don't have x to the third first. So all that's to say is we have to be a little bit careful. We don't just look at the very first number or the very first term. We look through all of the terms and say, okay, what's my highest power? So in this case, even though it's not the first thing that I see, my highest power is x to the 3, or specifically my highest degree is 3. And then the leading coefficient, the thing that is tied to that highest power, that x to the third term, is negative 6. I may have said it before, and I'm saying the definition a lot on this slide. A term is just a number and a variable by itself. So a has 3 terms, negative 2x to the 6 is one term, 5x is another term, and 1 is the third term. So I don't want to kind of keep using a word if I don't ever really define it. Now, The whole purpose that we're kind of went through those power functions is power functions are very specialized. You don't see a whole lot of expressions or equations or something that just has a single term, just has a single negative 2x to the 6, and that's it. It can happen, but it doesn't always happen. Well, the nice thing about this is that all of those rules that we came up with, that giant table with that end behavior, everything like that, can be used when we're doing the polynomial functions. And how we use them is we actually look at these two concepts, my degree and my leading coefficient, because those are kind of the strongest things, that's a very loose term, the strongest things in my function. So that's really going to drive what my end behavior is going to be. So again, I'm pulling down part A of example 1. I want to identify the end behavior. Well, I'm going to do that by looking at what my degree is and looking at the sign of my leading coefficient. Well, we saw my degree is 6. We saw my leading coefficient is negative 2. So we have a negative even function. So looking at this chart, pulled it over. Okay, bottom right, I have my end behavior for when k is less than 0 and it's an even power. So my end behavior will be as x goes to positive infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x also goes to negative infinity. Now, this part's a little bit of a review, finding intercepts. We've seen finding intercepts several times, but it is very important. It's worth repeating, so let's see it one more time. Well, I'll see it a couple more times in the semester, but let's see it an additional time right now. Okay, so finding my intercepts, it's always kind of, I plug in 0 for one of my variables and I solve for the other. So in this case, I'm going to start by finding my y-intercept. I plug in 0 for all of my x's. And I see that, okay, well, 0 minus 1 is negative 1, 0 plus 1 is 1, 0 plus 3 is 3. I multiply everything through. My y-intercept is 0, negative 3. Make sure if you're doing intercepts, you have to write them as points. Now to find my x-intercepts, I flip the process. I set my f of x equal to 0 and my y equal to 0, and I solve for x. Well, the nice thing about this is I don't even have to factor. It's already in factored form. So I can set each part equal to 0 and then solve, and it's just a one-step solving process, but I would say x minus 1 is equal to 0, so x is equal to 1. X plus 1 is equal to 0, so negative 1, 0 is an intercept. X plus 3 is equal to 0, so negative 3, 0 is an intercept. If it gets a little bit more complicated, if you have some more things flying around in your each individual factor, you should kind of write out the steps. I kind of just did a little shortcut. Okay, well, to determine my end behavior. Now, this is kind of a bit of a shortcut. So the long cut, and if you don't feel comfortable with this shortcut, definitely take this route every time. It's just more work. Is that if you have something in this form, if you have something already factored, well, what I can do is I can look at how many terms I have and if there's any powers associated with it. I'll term each factor. So the first factor, x minus 1, has a power of 1, there's that invisible 1. X plus 1 is a power of 1. X plus 3 is a power of 1. So if I multiply all of these things together, I know that I would have something of a power x to the third. And that is kind of how you should do it. You should multiply everything out. You should FOIL it. You have to FOIL once, and then you have to multiply a binomial by a trinomial, and it's certainly doable. But if you think about it for a little bit and say, okay, well, if there's 3 powers, I'm going to multiply it out, you know that you're going to have a power x to the third, and that's going to be your highest power. And maybe, I mean, in this case, it's not really that hard to see what k is, but maybe we have some numbers in front of our x's. That's perfectly fine. Really, we're concerned about the sign. So my shortcut is, okay, I see I have 3 different factors. I multiply them together, I'll get x cubed. And what's in front of them? Okay, well, there's a 1 in front of my first x, there's a 1 in front of my second x, there's a 1 in front of my third x. Well, if I multiply it through, I will have 1x to the third. I recommend multiplying it out, checking it, making sure that I'm not just making up stuff, but that will be your biggest term. And yes, there will be a lot of other terms down the line. And yes, they'll probably have maybe weird numbers. They won't all have ones in front of them. That's definitely true. But we know that doesn't affect our end behavior. The only thing that matters when we're talking about end behavior is our largest power, our degree, and our leading coefficient. So quite often, if it is in factored form, you can kind of logic your way through it and maybe write a little bit of work justifying your logic. If you don't want to do that, if you get stressed out like I do when you're taking tests, just go ahead and multiply it out. You will get the same result, and that is actually a much safer way to do it. Okay, again, that was long-winded, but in this case, 3 factors, multiply them together, I'd get a degree of 3, and I would get a leading coefficient of 1, which is positive. So now I'm going to look back at my chart. I pulled a piece of it. This chart, when I have a positive k and a degree of 3, that's an odd power. So my end behavior will be as x goes to positive infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x goes to positive infinity. Okay, turning points. Turning points, I don't want to kind of belittle them. Once we get into the very involved process, it's kind of built into if you've done everything right, you're going to get the correct amount of turning points. All of that being said, I'm pretty sure there's a WebWorks problem, and there might be one question on the test kind of relating these cute little properties, so it is worth mentioning. So a turning point on a graph is kind of exactly what you would see or what you think it would be. If you start to draw and let's say you're going up and then while you're moving down, that's a turning point. You're going down and then you have to move up, that's a turning point. And so a kind of cute relationship between degrees and turning points is that your minimum degree is always equal to your number of turning points plus 1. And we can kind of flip this idea. Your maximum number of turning points has to be equal to your degree of minus 1. So to see that in practice, this, if I'm just giving you a function, f of x, f times x to the 6th plus 3x plus 1, well, the degree is 6. And so if the degree is 6, I can have up to 5 turning points. Yeah, so using the second property, degree minus 1 will get me my maximum turning points. Now, a key word there, and I don't want to get a little bit too confusing because, again, this is more of a cute property versus something that we're going to see time and time again. But keywords here are minimum and maximum. So even though this property tells me that I could have up to 5 turning points, that is not a guarantee. In fact, this is what the graph looks like. I think roughly I may have change the coefficient slightly, but this is what the graph looks like. And so if I'm looking at this graph, starting from the left to right, I kind of draw up and then I take a small dip. So there's one turning point, then another dip upwards, and that continues up to about, I don't know, 0.25. Take a dip down, I take a dip up. So 1, 2, 3, 4. This has 4 turning points. That is not breaking my definition. It's just saying that if I have this graph, there is no way I might have like 20 turning points or something weird like that. So it's kind of a helpful way to maybe check your work or maybe think about the general shape of your graph, but it is very limiting because it doesn't guarantee that's going to be the number. You're not guaranteed to have degree minus 1 turning points. You're not guaranteed to have the number of turning points plus 1 is equal to your minimum degree. But I think I'm going to probably let you guys have a note card on the midterm. I might take a little bit of space on that note card just to write these down so that if a question shows up and it says, here's your degree, what can we say about the number of turning points? All you would have to do is say, okay, well, the number of turning points is the maximum number of turning points is degree minus 1. And again, I think it shows up on WebWorks, so maybe worth jotting down on your notes or whatever real quick, and then once you see it pop up on WebWorks, you'll be prepped for it. Oh, nice. All right. Yep. Yeah. Okay. Yeah. The actual degree is 6 instead of 7, but you know. Yeah. Okay, so for starters, we've seen this one before. We've seen, well, not the problem, but we've seen finding intercepts before. We saw it, in fact, in the last section. You always set one thing equal to 0 and solve the other. So in this case, I start by setting f of x equal to 0, and that means I can set each individual factor equal to 0 and solve. So x minus 1 is equal to 0, just add 1 to both sides. 2x plus 5 is equal to 0, I subtract 5 from both sides, divide by 2, I get negative 5 halves comma 0. And 3x minus 6 is equal to 0, I add 6 to both sides, I divide by 3, I get x is equal to 2, and so that intercept is 2 comma 0. And in fact, this is what the graph looks like. We could find the y-intercept. I'm not super concerned about that right now. We will see that in a later slide, but what's worth discussing right now in this slide and the next slide is x-intercepts. So that's what we're focusing on. And maybe just to kind of cover my butt, if I haven't already said it already or we haven't already seen it already, a lot of these graphs that I'm building or pulling from are made from Desmos. And pretty much any resource that you see me using in this class, if it wasn't done by me, it was done by Desmos or from the textbook. So I'll probably post that just to make sure I don't get in trouble. Okay, now when we're talking about x-intercept, sometimes we get a little bit lazy with our notation or our definitions, and we call them zeros, which does make a little bit of sense. It's when your graph is equal to 0. So my x-intercepts are each time that graph hits the y-axis, or y is equal to, sorry, the x-axis where y is equal to 0. So that's why we call them zeros, and that's why maybe your textbook or WebWorks is going to be kind of lazy, but just know when you see the word 0, think x-intercept. And so if we have an x-intercept with a multiplicity of 1, which means a power of 1, that means that my graph will behave as though at that 0 that it would just cross your x-axis. Where if I have a 0 of multiplicity 2, or my factor has a power of 2, then when I draw my graph, it's going to bounce off of that intercept. So in this case, my graph had an intercept at 2, 0. It's going to bounce off of that because it would have, hypothetically, a power of 2. I have a power of 3. We call this this is definitely not a technical term. I think we call it a wiggle, or maybe that's what I call it in my CU Denver class. But, you know, it's very similar to a cross. It's just a little bit wavy versus kind of a straight line through. And there are kind of properties that we could continue of like, what if the power is 4? Or what if the power is 5? You might have one question in WebWorks that has a power of 4. Just treat it as though it's a bounce. That's an even power. Even powers almost always bounces. So you would bounce it off of that graph. Okay, so to see these in practice, if I have a graph, I can kind of use that previous slide to talk about what the power of that factor will be, or what the multiplicity of it will be. So here I have a graph, I have a bunch of different x-intercepts. I don't really care about my y-intercept when I'm talking about multiplicities. We will see it later when we put all of these pieces together. And when we're talking about multiplicities, we're only ever going to talk about x-intercepts. So kind of looking at this graph, I have an x-intercept of negative 3, 0, negative 1, 0, and 2, 0. So we're going to kind of go intercept by intercept and describe what's happening at those spots. So let's start with negative 3, 0. Okay, well that's just a straight line cutting through my graph, or crossing through that x-intercept, crossing through that x-axis. So if it's crossing through, that means it will have a multiplicity of 1. My next point is my x-intercept of negative 1, 0, and it clearly bounces off of that intercept. So if it bounces, we say that has a multiplicity of 1, or that factor is going to be squared. Right there, circle it kind of later. And my third intercept that I see here is 2, 0, so that isn't going to cross, that isn't going to bounce, that is going to, for better or worse term, wiggle. It's going to kind of bend through that intercept. Now, believe it or not, we have all of the pieces that we will need to graph a polynomial. So these are kind of going to be the 3 steps. If you don't feel comfortable with any of these steps. We did identifying intercepts at the beginning. We just talked about multiplicities. And then we talked about end behavior, but end behavior was, I think, the last lecture, if not the lecture before. So we didn't talk about end behavior here. We talked about it previously. So if you don't feel comfortable with that, maybe go back and review that before we dive in here. So here is the polynomial I'm going to graph. Negative 2 x minus 1 squared, x plus 2. By the way, yes, this isn't kind of the general form that I wrote when I defined a polynomial the very first time, but it is still a polynomial because if I multiplied it out or simplified, I would get a polynomial. Okay, so that's all aside of what this actual problem is. So our first step is I'm going to find my intercepts of this function. The ending, but that's fine. So I start by plugging in 0 for all of my x's. In this case, I'm going to find my y-intercept. And 0 minus 1 is negative 1. 0 plus 2 is 2. And if I square my negative 1, I get positive 1, and that just boils down to negative 2 times 2, which is negative 4. Now, what I could do, and maybe I should do if I had a little bit more space on my slide, is I should take each factor and set it equal to 0 to find my x-intercepts. So I'll just kind of talk through it in this case. My two factors are x minus 1 squared and x plus 2 squared. So if I set x minus 1 squared equal to 0 and solve, I get x is equal to 1. So there's one of my intercepts. And if I say x plus 2 is equal to 0 and solve, I get my other intercept of negative 2 and 0. Now, I kind of offhandedly mentioned that we don't care about multiplicities of y-intercepts. We always just cross a y-intercept. So really, I'm only going to talk about my multiplicities with my x-intercepts. So my x-intercept 1 comma 0, I look back at my polynomial and I see, okay, x minus 1 has a power of 2, so it has a multiplicity of 2. And then my other factor, x plus 2, if I solve that, I got the intercept of x is equal to negative 2. In this case, there is no power displayed, but that means there's kind of that invisible 1, so the multiplicity is 1 in that case. Now, if we're going to talk about end behavior, again, the long-winded way and the proper way that we probably should do this is we should multiply everything out and simplify. So we would FOIL, and then we would multiply a trinomial, and then we would multiply everything by negative 2, but you're going to get the same results that I'm about to argue right now. Now, looking at my factors, I have x minus 1 squared, so I have 2 of those, really, in actuality, and then I have x plus 2. So if I were to multiply all of those things out, I would have the highest power I could possibly get is x to the third. And kind of building on that shortcut, anytime you are looking at a bunch of factors and you're trying to figure out your degree, you just take the number of each individual power and you add it together. So in this case, my first factor has a power of 2, my second factor has a power of 1. Put them together, my degree is going to be 3, or it's going to be odd. And now looking at the numbers that are in front of all of my terms, inside each factor I have positive 1, and I have a positive 1 right next to my x. They're the invisible positive ones. And then overall, I have that entire thing, whatever it's going to be once I multiply it out, is going to be multiplied by negative 2. So that means that I will have a leading coefficient of negative 2 if I were to go about multiplying it. Again, that's a very logical argument, and that's probably coming from the fact that I've seen this problem and problems like these hundreds of times. So if you don't feel comfortable, in all honesty, multiplying this out isn't super difficult, but if you get that kind of logic check, it might save you some time. Okay, so I have a k less than 0, my leading coefficient is less than 0, my degree is odd, so do I bring my table over? I do not. So looking back on my previous lecture, an odd negative leading coefficient means that my end behavior will, if I look at the left side of my graph, will be going to positive infinity, or my graph is going to start up. And as I go to the right side of my graph is going to go down towards negative infinity. So this is what I was talking about in the last lecture. As far as logic goes, when we're drawing a graph, it's good enough to just talk about, okay, on the left side, my graph goes up. On the right side, my graph goes down. Properly, you probably would have to do those definitions of as x goes to positive infinity, f of x goes to negative infinity, especially if that's specifically what the question's asking for. Okay, so now we actually have all the pieces. We have our intercepts, we have the multiplicities of our intercepts, and we have our end behavior. So for starters, if we're going to graph this, we're going to start by just plotting our intercepts. So my intercepts are -2, 0, 1, 0, and 0, -4 that we see here. And now what I'm going to do is, if I had a pencil, I'm going to start on the left side of my graph. So pretend that you're reading a book. So you're going to start on the left side of the graph. I'm going to look at my end behavior. My end behavior says my graph is up. So I would take my pencil to the top left point of my graph and just kind of start there in any general area. It doesn't have to be super specific. And then once I start there, I draw down to my first intercept. I'm going to kind of play connecting the dots here. So I draw down to my first intercept of -2, 0. And then I look at my multiplicity and say, okay, I'm at my first intercept. What do I do here? Oh, multiplicity is equal to 1. I am going to cross this intercept. So I'm going to cross -2, 0. And then I'm going to continue to connect the dots down to my y-intercept of 0, -4. And anytime we have a y-intercept, we cross it, so I don't even care what's happening with my multiplicity there. So I'm going to cross that guy, and I'm going to continue connecting my dots to my last intercept, 1, 0. Well, now I got to look. The multiplicity says 2. So multiplicity says 2. I have to bounce off of that intercept, and so I'm going to bounce off of that intercept, and I should finish bottom right of my graph, because that's exactly what the end behavior is telling me to do. So if I'm not following my end behavior properly, maybe I didn't sketch it right, maybe I didn't find my end behavior. So you got to kind of make sure that all of those pieces are fitting into place. So all of that talking gets me this graph. And yes, maybe the way I was talking through it, you didn't see that kind of big dip towards the left side of the graph. And maybe you just went from -2 to 0, -4. That's perfectly fine. It doesn't have to be super specific. Really, we want you guys to understand what's happening at those points. And that's exactly what I was talking about. It crosses -2, 0. It crosses 0, -4. It bounces off of 1, 0. And it follows the end behavior. Now, we want to, quite often in mathematics, if we're able to go one direction, if we have an equation and we can graph it, we should be able to go in the opposite direction. We should be able to take a graph and write it as an equation. And so we do that by identifying all of those important pieces of information again. So we talk about our intercepts, just looking straight up at my graph, not overthinking it. My intercepts are -3, 0, -1, 0, 0, 3, and 2, 0. Okay, well, the first thing we talked about last time was intercepts, or last slide was intercepts. Now we're going to talk about the multiplicity of each of those intercepts. So my first one crosses, so that's 1. My second one crosses, so that's 1. We don't talk about multiplicities for y-intercepts, so I ignore that part. And then my third intercept, or my fourth intercept, bounces, because it's got a multiplicity, so it has a multiplicity of 2 since it bounces off of that 2, 0. Great, so I found my intercepts, I found my multiplicities, and now the next thing I have to identify is my... Oh, no, I don't. So now I know that my function is going to build to, okay, I have 3 factors. And the factors are actually going to kind of be opposite of what our intercepts are, because it makes sense. If I were to set each term equal to 0, that's going to flip my sign. So my first term is, since my intercept was -3, 0, it's going to be x plus 3. My next intercept, since it's -1, would be x plus 1. And my third factor, since the intercept is 2, 0, would be x minus 2. And in this case, that last term has a multiplicity of 2, so I do have to square it. So now I'm kind of finding those pieces. All of those have to be intercepts, so they all have to be factors in my function. And I'm very close to being done in this step. The only issue here is I don't know if I'm multiplying this by something. So what does that mean? Okay, well, maybe the stretch is a little bit weird. That's kind of hard to see. Or maybe my graph is upside down. And so to account for that at this point, what I'm going to have to do is say, okay, this is kind of like finding the intercept in y is equal to mx plus b. You say, okay, I don't know what my a is. I'm going to put an a in front of my function. And then I'm going to find a point on my graph. One of the points on the graph that's pretty easy to use is the y-intercept in this case. Shouldn't use an x-intercept because everything would just follow to 0. But my y-intercept is perfectly fine. So I know a point on my graph f of x has to be 0, 3. So to account for that, well, I plug in 0 for all of my x's. I plug in 3 for my y, or my f of x. And then I solve for a. So if I go through simplifying, 0 plus 3 is 3, 0 plus 1 is 1, 0 minus 2 is negative 2. I'm going to square my last term. So then I get 3 times 1 times 4 gets me 12. So 3 equals a times 12. Divide both sides by 12. I get a is equal to 1/4. And then I kind of have to tie everything together with a nice bow on top of it and write my final function. So I think I did that. If we look back to the middle of the slide, yeah, exactly. If we look back to the middle of the slide, I'm just replacing that a with 1/4, and I'm good to go.